Now that we've looked at solving acid-base problems from an equilibrium standpoint, it's important to realize that every time you do the problem, you get almost exactly the same equilibrium expression. And so making the same approximations that we do when solving the full problem, we can arrive at a simplified formula that makes it quicker to calculate pH. Let's look at that for a weak acid problem. Here we've written out the problem in terms of a generic acid, HA, and its conjugate base A-. So that could be hydrofluoric acid and the fluoride ion, or it could be acetic acid and acetate. That's just any conjugate pair that we would like. So if we write down this expression, typically we're given a problem, here's a Ka and here's a concentration, what's the pH? So we can look at initially what do we have. So initially we say we have some concentration of the acid, and then we make the approximation that the H3O plus concentration is 0, and that the conjugate acid or conjugate base concentration is 0. But we know that the hydronium ions actually 10 to the minus 7. So our first approximation is we're just going to ignore that. Then we're going to say a certain amount of the weak acid will ionize. So we'll have some change. The protonated form will decrease by some amount, and the deprotonated form will increase by some amount. Because you can see what's happening is the proton's simply moving from HA onto the water, and so whatever HA disappears, A- has to be generated. Then at equilibrium, we have our initial concentration minus some very small change, X, and then the hydronium ion concentration will be X, and the conjugate base concentration will be equivalent to that. If we put that into the equilibrium expression, we get that Ka is the concentration of hydronium and the conjugate base, those are the products, divided by the concentration of the reactants, the protonated form of the acid. Plugging this all in, we get that that's X times X over C minus X. And now here's where we always make an approximation. We know this is a weak acid. Because it's a weak acid, it doesn't dissociate very much. The free energy side that's lowest is over on the left. And so X is going to be a small number. Number concentration minus a small number is approximately the same. And so if we rearrange this equation, we can find that X, which is the hydronium ion concentration, what we need to find the pH, is just approximately the square root of Ka times C. What approximations have we made? One, we assumed that 10 to the minus 7 was a very small amount to worry about, and that will be fine as long as we don't have super dilute solutions. And we assumed that X, the amount that reacts, is small compared to the initial concentration. Again, that's going to be true when it's a weak acid, so the smaller the value of K, the better, and the more concentrated the solution is, the better. We have the exact same idea if we look at a weak base. So here's a generic weak base problem. I've written it out with the conjugate acid, A-, reacting with water, making HA and OH-. You can see Kb now is exactly the same. If you run through the same analysis, you get the exact same result. And now with identical approximations, you discover that the hydroxide ion concentration is the square root of Kb, and now times the concentration of the weak base. So before we had a certain amount of acid and a Ka, now we have a certain amount of base and a Kb. Now we have a buffer situation. Here we have the protonated and deprotonated form. So we have two concentrations. One I'll write as HA and the other as A-. Again, we're going to ignore the very small amount of hydronium ion present. There's going to be a very small change, and in this case, again, because of Le Chatelier's principle, we have both reactants and products. The change will be very small. At equilibrium, we'll have the initial concentrations changed by some small amount, and the big difference will be in the hydronium concentration. And so if we plug that all into the equilibrium expression, making the same approximation that the changes from the initial concentration are small, concentration of HA minus X is approximately the concentration of HA, concentration of A minus plus X is approximately the initial concentration of A minus. We can rearrange this all and easily solve for the hydronium ion concentration. And this is the classic result for buffers and the Henderson-Hasselbalch equation. So that gives you 3 examples of how to quickly solve the equilibrium by making the same approximation that the change is essentially small, That works as long as the equilibrium constants are small and the concentrations are high. Some people want to know, when does it work and when doesn't it work? It never works. It's always an approximation. It just depends on how many decimal places you want. Pulling that all together, we end up with some very simple equations. For a weak acid, if you want to find the pH, you need the hydronium ion concentration. That's approximately equal to the square root of Ka times the concentration of the acid in the solution. For a weak base, the concentration of the hydroxide ion concentration is approximately the square root of Kb times the concentration of the base. If you have a buffer, you can either look at it from the perspective of an acid or from the perspective of a base. From an acid perspective, the hydronium ion concentration is Ka times the concentration of the acid divided by the concentration of the base, that is the protonated form divided by the deprotonated form. Or you can say the hydroxide ion concentration is approximately Kb of the concentration of the base divided by the concentration of the acid. That is the concentration of the deprotonated form divided by the concentration of the protonated form. And I realize looking at my little formulas here that there are capital A's and little a's. They're all the same. The acid is the one which is the protonated. The base is the one which is deprotonated. And since we can relate Ka and Kb with Kw, really all of these formulas are exactly the same thing, just like it was shown when we did the equilibrium problem. It's all the same equilibrium problem. It's just written down here in a shorthand. We could derive these same results for every single problem, but having done it time and time and time again, it's easy to jump to the answer now that you know how you get it.